Okay, so we will continue with an example. So let's look to this now. Okay, assume we have a program here, shown here. Okay. So how the execution will look like. So we will give a simple example. So assume we have the main memory, okay, addressed with those physical addresses, and we have the CPU. CPU has several registers, all right, general purpose registers and instruction register, PC register, and so on. Plus we will have base and limit registers, right, to keep track of the physical address space of a program. So base will be added to every memory reference that is generated by the program, for example. So now let's assume you have written such a program, okay. So that program is using logical addresses. It's a relocatable code, okay. So the logical addresses are like that. So it has some instructions addressed with those logical addresses, okay. Assume you have written such a program, or the compiler produced such a program. Here we see the assembly instructions, but actually consider them their machine code correspondent instructions, okay. So we have a machine code instruction, compare, another machine code instruction, move. So assume, consider their binary instructions. So now let's look. For example, this program can start from here and so on. Okay, it, for example, tries to move into register R1 a value in memory. Okay, from which location in memory? 28, right? So this is a memory address. So it's a logical address, right? What do we have actually at that address? Assume while you are writing this program, what did you consider while putting an address here? Yes, it's an address of a variable. Which variable it is? Right? So that you consider actually here you want actually as a programmer you want to move the value of x into R1. Okay, so you use, for example, such an address here. Okay, and here in that instruction you want to move into R2 a value, right? Which value you want to move? Y, right? You can actually, the address of y is 24, let's say, will be 24. The address of x will be 28, and so on. So you want to move the value of y into some address, into some register R2, for example, and you want to add the register and so on. So here we see a jump instruction, which has an immediate operand 16. What does it mean? You want to jump to address 16. Is the logical address or physical address? Logical address 16. So that means what do you want to execute after jump? Move, right? So we want to jump to that position in our code and continue execution from there, right? This is what you want to do, right? As a programmer. So now let's look whether when you run this program, is it the thing that really happen in the program, okay? So this program will be loaded, right? Into some position, start address. Into which start address it is loaded, for example? 24, right? So move instruction will have address 24, jump will have address 28, and so on, right? So assume the program is started to execute from here, okay? So this is compare will be the first instruction to be executed and so on. So the instruction will be fetched one by one. But before starting the execution, what do we have to do? When this program is to be run in the CPU, we have to load the base and limit registers, right? We have to load base register with which value? 24, right? So it will be the start address, physical start address, where the program has been loaded, right? What about the limit register? It has to be 32, the size of the program, right? It is 32. The size of the program is 32 bytes. Okay, assume. So those registers are set up just at the context switch time when you are switching context to that program, right? Then that program is to be executed in the CPU, okay? So instructions are fetched one by one, put into instruction register, decoded and execute and so on, right? Compare instruction is fetched, and then assume now we are at this point in our execution. At that point, so what we will do? Assume move instruction is fetched, put into instruction register. So what will happen now? So move instruction will be decoded. The immediate the operand, the memory address 24 will be detected, right? That means the CPU will now go to that address and fetch a value, right? So the CPU will use 28. So the operand is what here? The address is what? It's a memory operand, right? So memory address specified 28. So we have to go to address 28 and fetch a value, right? But this is a logical address. So CPU actually generates a logical address that has to be converted to a physical address. So a unit called memory management unit, okay, takes that logical address and converts it to a physical address. Okay, so what do we do there? How do we convert to a physical address? 28 is the logical address. Add to the base, right? Basically, we add the base register value to 28, obtain the physical address. So we add 28 with 24, and we obtain 52 as now the physical address, right? So this address is actually given to the physical memory chip. So the memory chip will return to you what? The value sitting there. So what is sitting there at physical address 52? Look at to the physical addresses at address 52. We have the integer x is sitting, right? So that means we can take the value of that integer from that address, and that address, that value will be now loaded, will be taken into CPU, right? So was that the thing that you want to achieve while writing this program, right? So in this way, by just relocating, using the base register and so on, by using base limit register and so on, actually, even though you actually loaded the program into an arbitrary location, the program will work correctly. While it's working correctly, what do you have here? All the addresses that are used here are the logical or physical addresses? The program content here is using some addresses, memory references. These references are logical or physical? Logical, right? So when the instructions are here, are actually executed, the memory references are made, memory addresses are used. Those addresses are logical addresses, right? But finally, at the time that that address has to be given to the memory to fetch a value or to fetch an instruction or put a value, at that time, that address is converted to a physical address. Okay? So this is what can happen in a system that uses logical addresses and physical addresses and relocation registers and so on. So as the programmer, you consider logical address space, just this address space. You write your program, place your program elements accordingly. Similarly, the compiler is thinking like that and so on, right? But at runtime, all those addresses are placed, are converted to physical addresses at the time that the memory reference is made, okay, on the fly, while the program is running, execution time. Is it clear? So the device that makes this translation from logical address to physical address is called memory management unit, okay? It's a hardware device that maps logical addresses to physical addresses. Those logical addresses are also sometimes called virtual addresses. So in memory management unit, the value in the base register, this is also called relocation register, the value in the relocation register is added to every logical address that is to be used by the CPU. And the user program in this way deals only with logical addresses. It never sees the real physical addresses, okay? So whenever the CPU makes a memory reference, generates a logical address from where we want to fetch a value, an instruction, or to where we want to put a value, okay? The CPU uses logical addresses because the program that it executes is using logical addresses. Just at the time, we add that value with the relocation register value and obtain the physical address. For every memory reference, we are doing that. Okay? Therefore, we are obtaining the physical addresses at runtime while the program is executing. So I have talked about dynamic linking a little bit. Okay? It means that a library is linked dynamically at the program startup time, not at the compile time. Okay? At the compile time, you are not linking with a library, a dynamic linking library. Like shared libraries are linked in this way. A shared library like standard C library is linked at the time of starting up the process, not at compile time. Okay. So linking is postponed until execution time. Small piece of code called stop actually used to locate the appropriate memory resident library routine. Stop replaces itself with the address of the routine. So the executable code contains just the stop, not the object code of the function. Instead of containing the object of the function that you are calling, it's just containing a stop. And that stop actually is replaced with the address of the function that you are calling. All right? And that function is executed. Any questions so far? So now let's look to another memory management idea, which is swapping. So we have seen that with the base and limit register support in the hardware, and assuming that the program can be loaded into some contiguous physical memory space, every program is loaded into memory in some contiguous memory space, right? So we can have multiple programs loaded and running concurrently, each program occupying a contiguous physical memory space, okay? So then we have multi-programming environment. We can do that, right? Memory management can be something like that. But let's look to this problem. Assume 10 programs are loaded into memory and memory is filled up. Now we would like to load a new program. There is no empty space in the memory. Assume each of these 10 programs that are loaded will just take 5 days to execute. Then are we going to wait 5 days to execute a new program? Or can you suggest something else? The idea is swapping, okay? A process that is loaded and will run 5 days, okay, can be swapped out, can be written back to the disk. The memory image can be just written back to the disk temporarily, okay? We say that it is swapped out of the memory to a backing store, to a hard disk, so that its space now can be used by some other process. And that other process can be given a chance of using the memory and running in the CPU, okay? So that the other processes doesn't have to wait 5 days. Then that other process can be given a chance, it can run for a while, and it can be swapped out as well. So we use for that a storage space, the disk space, a disk, okay? A fast disk can be used to swap out the memory image of a program. So that instead of that program, now another program can be loaded into memory and can run, okay? So this is the idea. You have a process, for example, that has to be running, for example, 5 days. Instead of waiting another process P2 for 5 days, assuming no memory is available, you can just swap that process for a while. So process P1 can be swapped out to the disk, and then process P2 can be loaded into memory and can be started and use the CPU for a while. And then it can be swapped out, and another process can be swapped in, and so on. And finally, again, process P1 can be swapped in and continue its execution. Okay, this is the idea, swapping idea. You just move the process as a whole from memory to the disk, and then later from disk to the memory again. Okay, swapping out, swapping in. Any questions? So, in this contiguous allocation, okay, if you are managing the memory with contiguous allocation, that means assuming the programs can fit into memory, into physical memory, you just take the program as a whole and allocate some space in the physical memory that's equal to its logical address space. It occupies that physical memory area, and the rest of the memory can be used by another program and so on. And at the same time, we have to have kernel inside the memory, right? So the memory actually can be considered a partition into two. One partition holds the kernel, resident operating system, all right, and the rest of the memory, physical memory, can be used to store the user processes, right? And relocation, base registers can be used to protect user processes from each other and from changing operating system code and data. Base register will contain the value of the smallest physical address that the program is using. Basically, the start address of the program in physical memory. And limit register will contain the range of logical addresses that the program may reference. And each logical address must be less than the limit register, and each logical address has to be added to the base register to obtain the physical address. The memory management unit does that addition, maps the logical addresses dynamically to physical addresses. So then we can have such a system. So this can be the hardware that is supporting this memory management. We have memory where we can load several programs in a contiguous manner. A program will be taking a contiguous portion of the physical memory. Another program will be taking another contiguous portion of the physical memory, okay? So when such a program is started to use the CPU base and limit registers will be, base register is the location register, will be loaded. Location register will be loaded with the start address of the program. Limit register will be loaded with the size of the program, logical address space size. Then that program will start executing in the CPU. It will make logical memory references. It will generate logical addresses. So that logical address will be first compared with the limit value. It should be less than that, right? If it is greater than that, what does it mean? It's an illegal memory access, right? So that program has to be suspended, stopped, terminated. If it is less than that, then we add the logical address to what? To the base address to obtain a physical address. Then we go to that location in memory and get the value or put the value or get the instruction, okay? Whatever the CPU would like to do with that logical address. It may correspond, for example, to a variable address, and the value of that variable is to be loaded from the memory. Then we go to that physical address, get the value, and load it into the CPU, okay? So the contiguous allocation then will look like this. The memory will hold some number of processes. Assume this process requires that much of memory, that process requires that much of memory, and so on. So here at this time, for example, we have the OS and 3 processes sitting in the memory. And each process is allocated contiguous space, right? So from time to time, what will happen? A process may terminate so that its area now will become available, empty. There we can load another program. The operating system can load another program, right? So for example, process 9 can be started and loaded into that area. Then process 10 can be started and loaded into that area, and so on. Then process 5 terminate and this area may become empty. Then process, for example, another process may terminate and that area may become empty. So this may happen, and after a while, if we look to the system, what we will see? We will see some partitions like that, some of which filled up, some of which is empty. Those empty partitions are called holes. So we will see some holes, right? Of course, if two holes are adjacent, they can be compacted, they can be combined into a bigger hole. Two holes cannot be adjacent. So then we will have holes that are scattered around in the memory, right? We can have holes, and also we can have partitions that are filled up with programs. So now the memory management will do what? The memory manager of the operating system will maintain the allocated partitions, which partitions of the memory allocate to whom, where that partition start, how long is the partition, what's the size of the partition, and so on. So that information is maintained by the operating system. Plus the free partitions. What are the free partitions? Where do they start? What are the size of them, and so on. Basically the whole list. It will maintain the list of holes, free partitions, that can be used for new programs, right? So the memory management with contiguous allocation will now include that. We can have a system that is actually applying this idea. Of course, these modern operating systems are not applying this idea. They are applying a more advanced idea. But this could be an idea, right? Managing the memory. So you can actually allocate contiguous space to processes, and you have to maintain the free list and so on, whole list and so on. So when a process arrives, it is allocated memory, right? From where? From a hole. So you have to search the list of holes and find a hole that is large enough to keep the program and load the program into that partition, free partition, or that hole, right? So what are the alternatives to do that? What is the algorithm to search for a hole? Assume now we have a request for loading a new program. A new program is to be loaded into memory. Assume the size of the program is n. Okay? The question is, into which hole or where can you load that program into in physical memory? So what the operating system can do is, it can just now look to the whole list of holes, and find a hole. So how do we look to the whole list? We have several strategies for that. First fit, best fit, and worst fit. If we apply the first fit strategy, we do this. We just look for a hole that is large enough to hold the program. First hole that is large enough to hold the program is selected, and the program is loaded into there. Okay, this is the first fit. In the best fit, you look to do all holes, all free partitions, and you find a partition, okay, space, free space, that is large enough, but also that is smallest. Okay, you try to find the smallest hole among all holes that is large enough to hold the program. Okay, in this way, you produce the smallest leftover hole. So what happens, for example, when you find a hole that is large enough to keep a new program, you allocate some portion of that to the program, and the remaining portion of the hole remains as a new hole, right? But that will be smaller than the original hole. So if you allocate using the best fit strategy, that means the leftover hole, the remaining hole, will be always the smallest among all possible choices, right? And we have another strategy, worst fit. In this case, you again look to the holes, all the holes, but now this time you select the hole that is largest and also that can keep the new program. So in this way you produce the largest leftover hole. Okay, people has analyzed those strategies and they found that worst fit and best fit actually better than worst fit in terms of the speed time to find a hole, and storage utilization, how well they can utilize the memory. Okay? Any questions about these strategies? Sorry. Okay, so we were at this point. So with contiguous allocation, with those strategies that surround, as a result, what we will have is fragmentation. You will have, at some time, holes that are very small, okay, so that you cannot load any program into them, okay, since the allocated storage should be contiguous to a program, okay, there will be useless holes, right? So this is called external fragmentation. You have some unused space. You have some unused space. And that unused space is external to the allocation. You have some allocated partitions, and in between you have, external to those allocated partitions, you have some unused space. Therefore, it's called external fragmentation, external unused space. Okay? How can you prevent that? Or what kind of action you can take to reduce the external fragmentation? You cannot prevent that, but maybe you can do something to get rid of external fragmentation. You can just move the partitions. You can just move the used partitions or allocate partitions towards one end of the memory so that you will have a large hole towards the other end of the memory, right? This is called compaction, okay? Of course, it is only possible if the relocation is dynamic, that can be done at execution time and so on, and also it takes some time. There is another type of fragmentation that's called internal fragmentation, meaning that sometimes you may allocate space to a program larger than the size of the program. Okay? Then some portion of the allocated space will be unused. That unused space will be internal to the allocation. So that's called internal fragmentation. Okay? Internal unused space. Any questions? So now we will start to look at more advanced techniques for memory management, okay? Paging and so on. So paging will be used for implementing virtual memory, which allows a program whose size is larger than the physical memory size to be run, okay? And we will see virtual memory in chapter 9. And virtual memory uses paging idea. So now we will see paging. And paging also good for eliminating the external fragmentation. If we have paging, we will not have external fragmentation, but we will have internal fragmentation. So, and also it allows us, the paging allows us the logical address space and physical address space of a program to be non-contiguous. With paging, the allocated physical locations or physical memory, the allocated physical memory to the process does not have to be contiguous. That portion of the memory may be available, you allocate that portion. And that portion also may become available that is not contiguous. You can allocate that also to satisfy the need of the memory need of the process. Okay? So therefore the allocated space to the process in physical memory does not have to be contiguous. So paging allows you to do that, okay? So what is the paging idea? So this is the idea now. With paging, you consider the physical memory to be divided into fixed size blocks that are called page frames or frames, okay? So you will determine the size of a block. It can be, for example, 4 kilobytes or 8 kilobytes. It has to be a power of 2. 4 kilobytes means that it is 2 to the 12 bytes, right? So after fixing the block size, you consider the physical memory to be divided into blocks, right? So you have then some number of blocks, physical blocks, free blocks available to you that can be allocated to a program. So you can number those blocks, or you can consider them as numbered, okay? So this is, for example, this is frame 0, page frame 0, frame 1, frame 2, and so on, okay? So frame 1, frame 0 can contain, for example, a page, right? And if the page size is 4 kilobytes, that means it can contain how many bytes? 4096 bytes, for example, okay? So the addresses there can be, byte address can be start from 0, it can go up to 4095 in page frame 0, and so on, okay? So we have some number of frames that means available in the RAM. So now we are considering the RAM as a set of list of fixed size page frames, okay, which can be allocated to a process. So a frame will have a size that has to be a power of 2, and all the frames have equal size, okay? And also the process. Now let's look to a program that's to be loaded. That program is also considered to be divided into fixed size blocks whose size is equal to the page frame size, okay? So consider the logical address space of the program as the user. Okay, you view the program memory as what? As a logical memory. All right. The variables, the stack, the instructions are considered to be sitting into such a logical memory. So they have logical memory addresses, right? So this is assume your logical address space. All right. All the addresses that the program is using are from that address space. Okay. Now that is also considered to be divided. The logical memory over which the program is operating, okay, is also considered to be divided into fixed size blocks. They are called as pages, okay, and page size is equal to the frame size. Pages and page frames. A page frame is a container, okay, that can hold a content which is a page, okay. So this is a content. Here we may have some instructions spanning a sequence of instructions, set of instructions spanning several pages. Sequence of variables, storage spanning several pages, and so on, okay? So that content has to be actually loaded somewhere in the memory in some physical page frames. So logical address space is also considered to be divided into fixed size blocks. And now what will happen? So when, for example, that program is to be loaded into memory, all right? The memory allocated to the program does not have to be contiguous. So assume at that time when that program is to be loaded, this is the memory state. There are some frames that are filled up, that are not available, and there are also some frames that are available, okay? So when that program is to be loaded into memory, what do? You search, you load the pages, right, that can contain variables or instructions, right? For example, page 0 can be loaded where? Into frame 1, frame 2, whatever you want, okay? So frame 1 is empty, so page 0 can be loaded there. And you mark that mapping. You store that mapping somewhere in a data structure called page table. You say that page 0 of the program is loaded into frame 1, right? Sorry, it is not to 1. And for example, page 1 can be loaded into frame 4. Then you have to have a mapping saying that page 1 is mapped to frame 4, okay? Similarly, you can load page 2 into some empty frame 2, page 3, page 4, page 5, and so on, okay? So all the pages of the program are loaded somewhere. That means some page frames are allocated to the program. And those page frames does not have to be contiguous, okay, anymore. But you have to have the mapping here. Since it is not contiguous, you have to have a mapping saying where each page is loaded. Okay? Here we have a set of contiguous pages, page numbers, but here the page frames are not contiguous anymore, right? And that information is kept in a page table, in a table, all right? For example, here we see an example. Assume we have this program, its logical memory that contains just 3 pages. As I said, the page size can be like 4 kilobytes. That means each page can hold 4 kilobyte worth of data or instructions, right? So this is the logical memory of the program that can contain instructions or data. So then assume those pages are free of the physical memory, frames are free. Those pages are loaded into those frames. And the mapping is installed, set up in a page table. So page table is just an array of entries, one entry per page here, telling where that page is loaded in the physical memory, where that page is sitting in physical memory, in which frame. So here it says that page 0 is sitting in frame 1, page 2 is sitting in frame 3, and so on. Is clear? So who is actually loading a page into some frame of memory? Who is loading that from the disk? The application or the operating system? Operating system, right? So therefore, after loading it, it knows, for example, where each page is sitting. And it is putting that information into page table. That means that page table is set up for that process by whom? By the operating system, right? And each process has its own page table. Each process has its own logical address space starting from page 0. Right? So page 1 of one process may be sitting here. Page 1 of another process may be sitting there. Right? So this setup of the page table for a process is done by the operating system. But what happens during the program execution? If you make a reference to a location here, a memory reference, that has to be translated into a physical address. Who is doing the translation? The operating system or what? Software or hardware? The translation has to be done by the hardware. The hardware will go to the page table, will understand that, okay, page 2 is actually located in frame 3. It will compute the corresponding physical address, okay? For example, the byte 0 of page 2, okay, will have an address around here, okay? And the corresponding physical address will be around here, okay? That computation has to be done by the hardware by looking up the page table. Is clear? So how do we do that translation? We will understand it with an example here. So here we have a paging example. So assume the page size is very small, just 4 bytes. In a page, assume you can just have 4 bytes. 4 characters can be stored in a page. So A, B, C, D, 4 characters can be stored in a page. Other set of 4 bytes can be stored in another page and so on, okay? So assume this is your logical memory into which you have stored something. How many bytes are there in the logical memory? 16 bytes, right? And assume this is the physical memory, okay? So again, physical memory is divided into fixed size block, and the block size is what? 4 bytes, right? Frames. How many frames do we have here? 8 frames, okay? So assume this is our physical memory into which we can load those pages. Assume those pages now are loaded here. So this is page 0, page 1, page 2, page 3. This is frame 0, frame 1, and so on, right? So page 0 is loaded where? A, B, C, D is loaded here, for example, okay? The content is loaded here. Sitting there. So that means we have to map page 0 to page frame what? 0, 1, 2, 3, 4, 5, right? So actually this page table is telling us that. So page 0 is mapped or sitting in frame 5. Page 1 is sitting in 6. Page 2 is sitting in 1, 3 in 2, and so on, right? So now let's look, for example, how we can address those characters or elements of the program. This can be a program or it can be an array and so on, right? So for example, F here may be an instruction, maybe an array element, and so on, okay? So F has an address of what? What is the address of F? 5, right? So logical address of F is 5. So we are wondering what is the corresponding physical address, okay? So here we can see immediately what the physical address will be, okay? F, the corresponding page is where? It is here. So the corresponding page frame starts at address 24, so address of F is 25, right? So here actually I can refer to an address with 2 things here. The page number, so actually that F is in page 01, it's in page 1, and what is the sequence of F in that page, or offset? So which byte it is? Byte 0, byte 1, byte 2, byte 3. So offset of f in that page is what? 1, right? It's called offset or displacement, okay? Relative position of f inside that page, okay? So this is the displacement. So basically, given the address, I can compute on which page it is sitting, which is on page 1, right? I can go to the table, obtain the corresponding frame number, which is 6, right? Then I can go to that frame, 0, 1, 2, 3, 4, 5, 6. And in that frame, the position of that character is the same, which is 1, position 1, right? Start position 0, position 1. Offset is the same, right? I can use the same offset there. So the offset is not changing, right? So the offset of a character inside the page is the same inside the frame, right? So let's do, for example, an example. So we have 16 bytes here. How many bits are required to address 16 bytes? How many bits are required to address 16 bytes? 4, right? So therefore, 4-bit logical addresses are enough to address this logical memory, right? So then, so each page here is just how many bytes? Each page is 2 bytes, right? How many bits are required to address the bytes in a page? 2 to the 2. 2 bits are enough. So since each page is 4 bytes, how many bits are required to address those 4 bytes? 2 bits are enough, right? So they basically 2 to the power 2. 2 is the number of bits required to address the bytes in a page. 2 to the power 2 will be the page size, okay? So what we can do is that we can use just these 2 lower order bits of a logical address to be the offset of that address, of that element. And the high order bits, 2 bits here, will be the page number. Okay? So whenever the logical address is given, for example, let's say it is 5. So 5 is what actually? In binary, it is 0, 1, 0, 1. So these 2 bits will be the page number, 0, 1. 0, 1 will be page 1, right? Is it really the case? 0, 1, yes, it is really page 1. Okay? So from the logical address, you can infer the page number and also infer the displacement inside that page. Okay? Then using the page number, you can, from the page table, obtain the corresponding frame number. And then you can concatenate the frame number with the displacement and obtain the physical address. Okay? This is how we obtain the physical address. And this operation, this process is done by the hardware. So let's give an example how we can convert a logical address 5, for example, to a physical address. All right? So logical address 5 is what? 0, 1, 0, 1, right? It is actually referring to, at address 5, I am storing f, right? So the corresponding physical address, how do we find it? So 5, the logical address 0, 1, 0, 1, what is the page number it corresponds to? 0, 1, right? 1. So actually it is on page 1, 0, 1. So the page number is obtained by how? By looking to these 2 bits, right? So page number is that. So I use that page number as an index to here. So looking up the page table is actually does not require to search it from. You can just use the page number as an index to that array and obtain the corresponding page frame number, which is what? 6, right? So that means now we have to go to frame 6. So frame 6 is what? So since we need 3 bits to address those frames, I have 8 frames. Okay, to address 8 frames, I need 3 bits. So each frame has an address or number that is 3 bits. So the frame number will be 110. So that frame number will be part of the physical address, and the rest of the physical address will be the offset, which is equal to the offset in the original logical address, right? Offset will not change because the relative position of the character inside the frame is the same with its relative position inside the page, okay? So then that will be our physical address, 11010. All right? What is that number in binary? So this is a number in binary. What is the value in decimal? 25, right? Is it really the case? So yes, F is actually at position 25. Okay, so it's correct. So let's do another example. Let's look, for example, assume we have a logical address which is 11. So what is the corresponding physical address? So what is the corresponding page number to 11? So in binary, 11 is this, 1011. So can you tell me which page it is in? 11 is 1011. What is the page number? 2, right? What is the corresponding page frame number? Page frame number 1, right? So in the physical address, the page frame part will be what? 001. What about the displacement here? What is the displacement? Offset. 1, right? In the frame, physical frame, in the physical address, the offset will be the same, right? 1. So now this will be our new physical address, which is 111. So it is 7 actually. I go to position 7 here, which is here, okay? So I have the character L, right? Did I have, for example, L at the same position here, 11? At 11, I have also the character L, okay? So let's do another example. Let's consider the address as 13. So what is the physical address? So 13 is in binary what? 13 is in binary this, right? 1101. So what is the corresponding page number? So what about the corresponding frame number? 2, right? So therefore, the physical address will start with what? Right? 010 is the frame number, and then concatenated with the offset. Then that will be the physical address. So in general then, from this example, the general algorithm is this. So this is done by the hardware with every logical address. So address generated by the CPU, logical address generated by the CPU is divided in 2 partitions, page number and page offset part, okay? So an address that is, for example, n bits long, okay, is divided in 2 parts. N bits of offset part and n minus n bits of page number part. So if, for example, offset part is n bits, what is the page size? Can you infer the page size? 2 to the n, right? So depending on the page size, you can understand how many bits are required for the offset. And the remaining can be, for example, page number part, right? So you divide the address into these 2 parts, and that part is now considered as the page number. That part is considered as the offset. So that part, page number, is now used as an index into the page table, okay? So page number part, P, the value stored there, you see some bits here, right? You consider those bits as a value. That value is the page number. That value will be used as an index into a page table. You go to that location in the page table and retrieve the frame number. And that is to be concatenated with the offset to obtain the physical address, okay? So that frame number actually can be considered as the base address of each page in physical memory, into where the page is loaded, okay? So page offset combined with the base address, that frame number, it will be combined with the page offset to define the physical memory address that is sent to the memory unit, okay? So actually this hardware operation will be illustrated with this diagram. So CPU will generate a logical address. So this is the logical address, okay? So the whole thing is a logical address, some number of bits, let's say 32 bits or 20 bits, okay? Or 16 bits. So it is divided into 2 parts. That part is considered as the page number. That part is considered as an offset. Okay? So displacement D. So that value here in that part, P value, is used as an index into the page table, right? So the hardware is just looking. It's just considering those bits, using them as an index to the page table sitting in the memory for that process. All right? In the kernel. And then, at that location, at that index, we see a value. For example, here each page table entry can be 4 bytes. We can see a 4-byte value here. That will be considered as a frame number. Of course, the number of bits here should be equal to number of bits for the frame number. It doesn't have to be equal, sorry. So we can obtain the frame number here. And after obtaining the frame number, we concatenate what? The displacement or offset bits. And then we consider this as the physical address. Then we just give this to the physical memory and try to retrieve an item from there, value from there, or put a value there, or maybe retrieve an instruction from there, okay? So that will be our physical address. Is it clear? How how you obtain the physical address from a given logical address. And this operation is done by the hardware. Setting up this page table is done by the software, by the operating system. But then use of it while the program is running, making memory references, it is done by the hardware, because that has to be very fast. Obtaining the physical address from the logical address should be very fast, because you are doing it with every memory reference. For every instruction that is executed in the CPU, you at least make 1 or 2 memory references. At least to fetch the instruction, you use a memory address. Then it may include a memory operand. Then to fetch that operand, you use another memory address. Each of these require a translation from logical address to a physical address. Therefore, it has to be done in hardware to execute the instructions fast in the CPU. So at any time, what we can have then free frames and used frames in memory. Initially, for example, assume this is the memory, physical memory. Some frames are used, some frames are empty. These frames are empty, okay? And any program is to be loaded that has 4 pages. So here we have the operating system will maintain which frames are free. So the operating system can maintain such a list, okay, indicating which frames are free. So when that process is to be loaded, then for each page it can allocate its frame and load the page to that frame. For example, page 0 is loaded to frame what? 14, right? Page 1 is loaded to frame 13 and so on. Page 2 is loaded to frame 18 and so on. So these will become used. So now we only have, after loading that program, just 1 free page frame, which is frame 15, right? For example. So then the program is loaded. Of course, while loading them, the operating system is also setting up the page table. Whenever you load any page into some frame, you store the corresponding mapping from the page number to the frame number in the page table, okay? Any questions? So we will continue with the implementation of the page table and so on in the next lecture, all right?